Okay. Gradients, these are the two main properties of the gradients. What are the states? Blah, blah, blah. Blah, blah, blah. Blah, blah, blah. Alaska, Iowa. This is Iowa right here. And then where were we here again? This is, we started from Missouri. MO, right? Missouri? And then we talked a little bit about something there. Sorry for whoever's listening. And then this picture. Okay, so that's what happens when I forget. Okay, so we have those two ideas from the gradient. We got those two facts. Okay. Last thing we talked about, I think, if I remember correctly, I don't have to remember because I can just look at our notes. If I can find the notes. The last thing we talked about was the idea that if you had a three-dimensional function, or a function with three variables, then the gradient is a three-dimensional vector that gives you the perpendicular vector, right? And I think we had a cool example over here. Where's our example? Oh, I can't find our example anymore. All right. So let's take this this idea and then let me do something to this idea that might seem a little strange or weird. So basically what we said last time is that if we had a function going from R3 to R, then our gradient is perpendicular to a level set. Right? So if that's true, let's take a look at a function that we did. Oh, I left it at work in my office. Let's take a look at this function. Let's call it G. So let's take a look at this function. And this, how would you describe G in terms of this notation? G colon what? G goes from R, what? R cubed? No. R squared. So R, it's not called R squared, R2. It's kind of funny because I get mad at the algebra students for saying x2 when it should be x squared, right? But here, this is not. You're not squaring it. It's R2, yeah. So you're not doing it. Oh, I don't have a D2. So in this particular scenario, when we talk about the gradient is two-dimensional, right? It has two components, the partial of x with respect to a partial of g with respect to x. and then the partial of g with respect to y. And so if we were to continue talking about the gradient's properties, that it's perpendicular to a level set, in this case, this is perpendicular to a level curve. And what we could do is we can draw level curves, and we might have done this already. Just draw level curves and then find some vectors and place them on those particular points, and we'll see that it's going to be perpendicular to a level curve in 2 dimensions. So what does that have to do with what we're doing up here? Well, are you guys asking that question? I hope you're asking that question. Because what it has to do with this is that we can look at this function as z is equal to x squared minus 3xy plus y to the 4th. And then, if for some reason you want to bring the z over to the other side, we're going to get x squared minus 3xy plus y to the 4th minus z is equal to 0. Now, if you stop and think for a moment and look at this information up here on top, what we have just created is a function of x, y, and z, a function of 3 variables. That's equal to a constant. So what we have here, this is a level set. Instead of generically saying set, it's specifically now a surface. So this is a level surface. Well, I think you can call it set if you want to be generic about it. But if you have something specific, like I know this G goes from R2 to R, I will call that a level curve. And if this particular case, in this particular case, my F goes from R3 to R, and if that's equal to a constant, then that's a level surface. Now, this idea is kind of mathematically weird or strange. And we were just talking about this very same function as a function of 2 variables and looking at level curves. And now, all of a sudden, I kind of brought it up to a function of 3 variables, and now we're looking at a level surface. And what I want you to do is just think about that for a moment and understand that idea of what we're doing. And see if you can come up with any questions for me that's not clear. Any questions? So no questions means it's crystal clear, or it's so damn confusing I don't know what to ask. Which one is it? Rick has a question. Let's see. What's up?
So what does 0 represent? That is like flat?
So 0 in this case would represent a level set for a 4-dimensional function. So we're imagining this is now in 4 dimensions, and we're saying we'll let W, which is what our usual variable for 4 dimensions, we'll let W equal to 0, and then what I get is a resulting surface. Remember, looking at W is equal to f of x, y, z in 4 dimensions is impossible for us. Unless, you know. What? Chris has a question. What's the question?
Oh, my question was, can you now subtract, you know how you subtracted the z, can you now subtract the w?
Yeah, we're not going to do that. That gets even weirder. But yes, we could do that, and then we can look at it as something in 5 dimensions. Yeah. But we don't.
So you
you can do that. We're not going to. Because what we want to do is we want to stay in sight of this particular surface. Because this was a surface. We're looking at the same surface. That's the big deal. Is that this surface that came from a two-dimensional function is now a surface that we can express in 3 dimensions. Say it again? You can do that to any 2-dimensional, 3-dimensional function. Hell, we can do it in like in R2, R1, R2. Should we do that real quick? And I'll come back to this idea. Yeah, see if we can visualize this. Let's take a little detour. Should we call it a detour? I would call it tangent. Let's go on a little tangent. But never mind. Let's take a look at y equal to x squared. We know this. We've studied this inside and out. And so we know that this is a curve. And then we can even look at this as y, or f of x, is equal to x squared. Okay? So now that we got introduced to functions of several variables, more than one variable, we can actually, maybe I should call this g. Let me call this g. Just to be consistent with my previous example. So now, if I consider a new function, f, but this time of 2 variables, x, y, and I say this is equal to, I'm going to change it up a little bit, y minus x squared. I can look at that as a 3-dimensional function, right? In fact, we can draw this as a 3-dimensional function. No, it would just be a z is equal to it's a 3-dimensional function, so z is equal to this. So, in fact, I pulled out my graphing calculator program to see if I could just graph this. Z is equal to y minus x squared.
Why would you subtract x squared instead of y?
I guess to make a little bit of a point, that I randomly selected 0 for my previous example. Here I'm going to select something else. Can I select something else? I don't know. All right, let's do what Cameron's saying.
So for the previous example, it was z equals x squared minus 3xy minus y to the 4th. So you're saying that you can take that whole chunk and subtract the other side, so it would be z minus that whole thing?
Yeah.
Okay.
Yeah, you could do either one.
Sure.
Yeah, because if you multiply by -1, it's still the same equation. All right. So we're looking at this 3-dimensional function, but what I'm concerned about, or what I really want to do, is just look at a level curve. So let's take a look at the level curve when z is equal to 0, and for that, I mean to say that if we take a cutting plane, z is equal to 0, I want to see what the image looks like. So if I take that cutting plane, z is equal to 0, I basically have y And then I'm going to put primes because this is going to be a dual picture here. Y minus x squared equal to 0. So I have this graph over here, which is the graph of the intersection of that surface and my cutting plane. And then if you notice what this graph is exactly y is equal to x squared. In fact, if you look at y minus x squared is equal to 0, you can just, arrange that to make it look like y is equal to x squared. So, I essentially went up to another dimension and found something in 3D and then brought it back down to 2 dimensions to come up with the same picture. So does that idea make sense? All right, so what we did here, or what we're trying to do here, is that we have something here that is in 3D, right? I added another dimension to it, so now this is in 4D, but then I'm taking a level set of that, so it essentially becomes a level surface. Now I'm back in 3 dimensions. So imagine being in 2D, going up to 3D, and then taking a slice of that, so now I'm back to 2D with the exact same picture. So that's what's happening here. Okay? Is that okay so far? All right. Why would I do that? Well, I know that the gradient is perpendicular to a level set. So it must be that when I take the gradient of this, it's going to be perpendicular to a level surface. And I have this level surface over here that's exactly the same level surface that I've been messing with. Actually, the same surface that I've been messing with. So let's take the gradient of this thing to help us find a perpendicular vector, a vector perpendicular to the surface. So the gradient of this without evaluating the x, y, z values yet, the gradient of this is going to be 2x minus 3y minus 3x plus 4y cubed. There's 3 components to this gradient, right? Partial of f, partial of x, partial of y, partial of z. So partial z, there's 0, there's 0, there's 0, there's negative z there. So the derivative of negative z with respect to z is what? Negative 1. Where did the negative 1 come from? All right, more specifically, if we want to be at 1, 2, I didn't know what the z value is, but well, it doesn't matter. I guess there's no z in my gradient. So this gradient is supposed to be a function of three variables, x, y, and z, but when I took the derivative of z, it disappeared. So it turns out that it doesn't really matter what z is equal to. So if I have 1 for x and 2 for y, my gradient is going to be -4. Anybody? 29? -1. Does it look familiar? For those people that got it correct. Okay? Now we have a vector that's perpendicular to the surface. Now, let me show you how this thing looks like in general. If you have a surface g of x, y, z, or x, y, let's say z is equal to that. This is your surface, right? So this is a g function that goes from R2 to R. And then I bring this up to a higher dimension and call it f. Now I have a function f of x, y, and z is equal to g of x, y, which is equivalent to like that big mess that we had in our previous example. And then I'll bring the z over to the other side, minus z. Where now I have a function f going from R3 to R. And now I'm going to consider the level surface when instead of calling it W, I'm just going to rewrite f of x, y, z equal to 0. And so what we essentially have is g of x, y, minus z. G is a function of just x and y, and then the minus z was brought over to the other side from the original surface. And if you set that equal to 0, then it is exactly that same surface. That level surface here, we're calling it a level surface, is actually exactly the same as the surface up above. And so the gradient of f now of f is equal to, I want to take a look at this expression over here, or this expression over here, and take the derivative of this with respect to x, with respect to y, and with respect to z. Now the derivative of this with respect to x, the z over here is a variable on its own, and there's no x's there, so I just have to focus on the derivative of this thing with respect to x. So I think that's the derivative of g with respect to x. Switching notations on you from Leibniz to the subscript notation. The derivative of f, which is this whole thing with respect to y, is just a derivative of g with respect to y, and then this other part does not have any y's in it, so that goes away also. Now the derivative of f with respect to z, when I take a look at the g is only a function of x and y. There's no z's in there, so that would be 0. And then the derivative of this with respect to z is what? negative 1. So this normal vector is given by the partial of x, the partial of y, and negative 1. Now last time we have a negative 1 pop out. Where did it come from? What? Yeah, so back then, how did the negative 1 pop up? The same negative 1. We crossed it. It came from a cross product last time, right? Yeah. So now what we're doing is that from another approach, instead of taking a look at two tangent vectors and crossing them, we're taking a look at this from another dimension, from another point of view, by going to a higher dimension and looking at a level set, and we're getting the same result. I'd like to think that's pretty deep, but it's constant with respect to x and y, so that's why when you took the derivative with respect to x and y, you don't really consider it. But z now, we're looking at z not as a constant, but as a variable for the new function when you brought it up a level. Oh, if z had a constant next to it, then it would just be treated as 0 when you take the derivative. It'll still go away. It would be when you took derivatives. So the point here is that we're taking derivatives to get our gradient. And so if you had an extra constant laying around, it'll go away. So whether it's attached with a z, and we don't have a coefficient. If it was like 2z, we won't have that because we're looking at this original surface function, which is z by itself. All right? Okay. Does that make sense? Okay. It makes sense to a handful of people. The rest of you guys are either falling asleep or totally lost. And if you can come up with a question, be more than happy to answer. I have office hours also on tomorrow morning, 9:30 to 10:30. If you want to come up and ask questions, or you can ask your classmates. You can email me questions about this. But all right, whatever. Yeah, look back at our old notes to see where the negative 1 came from. And here we did not do any crossing of anything, right? And we're still coming up with the same normal vector. So the normal vector is a partial with respect to x with respect to y and negative 1. I think that's interesting. Doesn't matter, and a lot of times I won't ask you to derive it. I just ask you for the normal vector, in which case I think this is easier than having to find them and cross them, unless you're asked to actually find them first. But even then, you should know what the normal vector is. All right, let's go off to a new section. I think it's 7 now, and we're dealing with max and mins. Yeah, calculus is a study of the rate of change of things, but one of the biggest things that you learned back in Calc 1 was optimization, as finding the maximum and minimum values. And if you remember back in Calc 1, let's list the things that we remember in Calc 1. How many people would have a blank page? Just kidding. You know something about Calc 1, right? you spell calculus. C-A-L. Let's find ideas about maximum and minimum. When you first started studying maximums and minimums, you already know how to take derivatives and stuff like that. When you started studying about max and mins, what was one of the first things that you found, or what that you had to look for? No. What? Derivative equal to 0. Is there a special name for that? Critical point. We took the derivative, we set it equal to 0. You guys mentioned the second derivative. What was that used for? Concave up, concave down. So I'll put it down here a little bit because I want to squeeze something else before the second derivative. Second derivative allowed us to find the concavity, and I was going to write a few more things down here, but I'll hold off on that. But before we studied the second derivative, there was something else that we did in terms of max and mins. Inflection point, that's kind of falling close to the derivative idea, the second derivative idea. Yeah, what's that called? Got the number line, you got a critical point here, positive to negative or negative to positive. There's a special name for this particular thing. Anybody? No. Well, the first? First. What? First what? First derivative? Test. First derivative test, we called it. What?
I've never heard that before.
Never heard that before?
I mean, I've done the number one.
Okay. This was called the first derivative test. We found a critical point. We checked points around it, see if they go up and down to the left and to the right. And then we found whether it's maximum or minimum. And it turns out that if they both go down, then it's neither a max or a min, right? That's happened. And there's a good chance that that's an inflection point, which may or may not be. But we studied inflection points down here when we started to do second derivative. But there's a second derivative, not just the second derivative, but the second derivative test. Do you remember what the second derivative test was? It's one of those things where Calc 1 teachers really focus on the first derivative test because that works all the time. It turns out that the second derivative test doesn't work all the time, so why really bother looking at second derivative test when if it doesn't work, you have to go back to do the first derivative anyways. So let me ask you, how many people remember the second derivative test? What does the second derivative test say? So I take my critical point, C, let's say C is my critical point, and I put this into my second derivative, and then I have to look at my answer. So if my answer looks like, if I put this in the second derivative and I got a positive number, that means that it's concave up. If it's concave up and it's a critical point, what can you say about the point itself? It's a minimum. If it's concave up, and this is your critical point, which has a slope of 0, because that's how critical points are defined, then it must be down all the way down at the bottom. And if you put this into the second derivative and you get a negative number, that means it's concave down, which means it must be sitting up on top as a maximum. Now the deal is, if it's equal to 0, we cannot conclude whether it's a max or a min. It could be a max, it could be a min, it could actually be neither. Right? It could be an inflection point. So if you just take a look at x squared as an example, negative x squared as another example, and x to the third, those three examples give you the three different scenarios of no conclusion. So then, you as a student and the teacher as a teacher would say, well, if there's no conclusion there, you have to go back and do the first derivative test. And so you as a student would say, oh, why don't we just use the first derivative test in the first place? And then the teacher would say, yeah, okay, go ahead. And so the second derivative test kind of gets put in the background and kind of disappears. But that's okay, because your third semester calculus teacher will remind you what the second derivative test is. I just did that. All right, let's move on. Because now we're in Calc 3. Keeps calculus. So in Calc 3, we're going to do the same thing. Well, let's see if we can make our parallel comparisons here. We're going to define a critical point. Let's do that right now. So remember, though, our function that we're dealing with has two variables now. The function that we're dealing with has two variables now, or more, but let's just deal with two variable case for now. The functions that we're dealing with now have two variables, so when we say derivative, we have to specify, oh, is it the partial with respect to x or partial with respect to y? So in that case, we're going to need to put both of those criteria as part of our definition for the critical point. So a point, and this has to have two variables, right? Or two components. AB is a critical point. If not just the derivative with respect to x, but also the derivative with respect to y. And we're talking about partials here. So both partial derivatives have to equal to 0. That's our that's our condition for a critical point. Okay? Now we have a critical point. The first derivative test looks at the critical point and then looks at points around it, to the left of it, to the right of it, to see if it goes up or down, right? Which is what you guys did a lot in Calc 1. Now let's imagine doing that for a surface. Did you imagine? What did you imagine? Lunch? What you guys were imagining right now? What were you guys imagining? Sleeping? Oh, I'm imagining spring break right now. Boy. All right. First derivative test. I guess the question is, how would we do the first derivative test here? So, yeah, what? Well, remember, the domain, we're focused on the domain, which is back in Calc 1, it's just an x-axis. It's just a one-dimensional axis. Your domain here is a plane, and your surface would be whatever the surface might look like. But if you imagine the plane, and points around the plane, points around that special point that you have, there's a lot of different ways to go. Remember limits when we're talking about limits? Paths. We can do paths along the x, along the y, diagonal lines, and then curves. There's too many paths. There's too many paths to consider. So it turns out that there is no, quote, first derivative test. So there's no first derivative test in Calc 3. That's too bad because that was pretty easy back in Calc 1. And the reason why they do talk about the second derivative test in Calc 1, even though you don't use it very much, is because that is a test that will carry on over to higher dimensions. So in Calc 3, there is a second derivative test. Now, the other issue is that when we talk about, since we're talking about a function of two variables, when we're talking about second derivatives, what are the second derivatives in Calc 3? We briefly talked about it, really quickly, and that's the partial derivative of x with respect to the partial derivative of x. Wait. Yeah, remember there's like 4 derivatives now. There's 4 second derivatives involved. There are 4 second derivatives. There's fxx, fxy, fyx, fyy. And so there's 4 derivatives, and if we bring this conversation about concavity going on here, we have to look at this. The concavity is like something to do with a parabola, the best parabola fit in terms of Taylor polynomials. And here we would have to consider some, I don't want to put the vector brackets there, I just want to put a set bracket. We want to consider a 2-variable paraboloid that would try to mimic this particular function, whatever this function f is. And that is kind of hard to visualize, to see. So what we're going to do is we're just going to copy the book. We're just going to set the criteria for these things being positive or negative. So let's put the second derivative test here where there's more room. And for this, we'll set it up like a critical point. Let's say we find critical points. Let AB be critical points. And by definition, you have to find the first derivative with respect to x, with respect to y, set them both equal to 0. So finding the critical points in itself is going to be a challenge for us. And so we'll start doing those problems after we get this down. So we got critical points. And then let's define discriminant, determinant, discriminant. D is probably not the best letter to do this. So let me check what the book says. They use D. Yeah. M? Yeah, let's use D. All right, D is a discriminant, and let's define this discriminant as f(xx) times f(yy) minus f(xy) times fyx. Now, I'm not going to write that down because if we're dealing with these nice functions that I've mentioned before that we're going to be dealing with, these called mixed partials, they're called fxy and fyx, they're going to be the same. So let's put that as a little side note. So fxy and fyx are called mixed partials. And for nice functions, functions that we're going to be dealing with, we're not going to be dealing with functions that aren't nice. So for nice functions, fxy is equal to fyx. So really, this comes from, the discriminant actually comes from a matrix of partials. And since we've already talked a little bit about linear algebra and determinants of matrices, it's okay to mention this. It's not that big of a deal if you just memorize the discriminant formula, but it really comes from finding the determinant of this matrix of mixed, or matrix of partial derivatives, second order partial derivatives. So there's fxx, fyy, minus fxy and fyx, which are the same, and so they're just written like this. So that's D. Yes? Well, if you didn't have a nice function, you probably wouldn't have those critical points there, or some other weird thing happening. All right, so this is still part of the definition. Now we make our conclusions. If, conclusion number 1, if your discriminant is positive, by the way, these things should all be evaluated at AB. And fxx is also positive. then something. So positive, positive, it's concave up, so it's going to be a minimum, right? Then AB is a local minimum. Now, the way they check the signs of the second derivative is kind of weird here. It's a combination of the discriminant and fxx. So here, where the discriminant is still positive and your fxx, the second derivative with respect to x and then with respect to x again, is now negative, then your critical point is a local maximum. Now, if your discriminant itself, the discriminant that we're looking at, is less than 0, then you don't have to check the fxx. You just come to the conclusion, and your conclusion is that the critical point is called a saddle point. And if you remember what a saddle looks like, it looks like from one side it looks like it goes, it's a minimum of a parabola. From another side it looks like it's a maximum of a parabola. Think of a saddle that you ride on a horse or a Pringle. And usually most textbooks stop here and say, okay, that's the second derivative test, period. But I want to include this last one to show the analogy for the second derivative test in Calc 1. And that if your discriminant actually turned out to be 0, then there is no conclusion. Okay, so you did all that work for nothing. You have to find other ways, which we don't have, to determine whether you have a maximum or a minimum at that point. I should check to make sure I did that right. Positive, positive, local min. Positive, negative, local max. Here they say it's neither a max or a min, but it's a saddle point. And then they don't mention when it's equal to 0. Okay. So I think this is a complete set for your second derivative. And what we're going to do next time is we're going to find local max and mins, and then we'll talk about when you would have the absolute max and mins, and then how to find those. Okay? All right, that's it for today.